of the slides. What's getting added is shown in the lower left-hand corner. What we are studying are our benzene structures. So how do we name a benzene structure? Typically, when we're talking about the nomenclature of these aromatics or benzene structures, they get called benzenes. Right? And so what we would do is name the substituents attached to the benzene. So there's 6 carbons in the benzene with all of those double bonds. That's a pretty high priority carbon structure, and so usually it carries the root name. Right? So if we took a look at these two structures here, what we now need to go through and do is name what the substituents are on those ring structures. Well, in this first one, what's the substituent? Chloro. So, or chlorine, which becomes chloro. So it just gets called chlorobenzene. Super creative. The next one? A nitro. So we get nitrobenzene. Okay. What if we made it slightly more complicated? And now added a CH3. What do you mean, oh wait?
1-chloromethylbenzene.
Where's the methyl? Okay. So 1-chloro, 2-methylbenzene. Why not 1-methyl, 2-chlorobenzene? Okay. Deciding that priority could become a little bit difficult, as Mustafa just pointed out. We've got the alphabet that we've got to fall back on, which clearly I need to practice. Chlorine or chloro comes before methyl, so the chlorine should get the number 1. In all honesty, I'm not positive on that because that's how weak I am with nomenclature, but I think you would be correct if you broke the name down that way. As Alex was about to shout in, though. Could we reference this as a phenyl? Okay, and so what you're saying is, isn't this a phenyl? No. Okay. If we wanted to reference this attached to that methyl as the main group, we could call that phenylmethane, where the main group was a 1-carbon structure with a phenyl substituent. Okay. Is that allowed? Yes. Then it is a phenyl. Okay. And this is where this is going to become challenging, and we'll discuss it. So we could call it phenylmethane. The problem with that is that we're now naming as the root structure a smaller piece than our substituent, and that doesn't make logical sense. Does that make sense? Okay.
Also,
and we'll address the chlorine a little bit later. Yes?
Also, if you did that, you wouldn't know where the methyl was.
If we said phenylmethane, where's the methyl on the phenyl? And really, it's actually where's the phenyl on the methyl. By definition, at position 1, it wouldn't matter. Okay. The real question is then where's the chlorine on that? And we could address that. Okay. If we were going to stick with this name, which is awful, but nomenclature is awful in general, so why the hell not, right? Okay. The chloro would have to go out front. The chloro is at position 2 of the phenyl, so we'd have 2-chlorophenylmethane. God, that name is awful. Okay. We could do that. Okay. That's not the greatest name. Okay. You're now putting more weight on the 1 carbon as your main chain versus the phenyl or the substituent, and that doesn't make sense. Okay. So the largest chain in that case makes more sense to put as the benzene. Okay. Whoops. And of course I deleted the methyl. So there's our benzene. What was the name you gave me, Mustafa? 1-chloro?
Yeah, 1-chloro,
2-methylbenzene. 2-methylbenzene. Okay. So that could work. Okay, because we brought up this option of a phenyl. Let's push this a little bit further and make everybody super irritated with nomenclature, so you can all agree with me that nomenclature is the devil.
If you had another ring, could you call it?
Let's not make that worse yet. Okay, you're just making what I'm about to make worse, like exponentially worse. Don't do that yet. Okay. Okay. That piece tends to be very, very common, and so that piece can carry a common name associated with it. The common name for that piece is toluene. Okay. So where's the chlorine? Well, the chlorine's attached to the toluene, so I could call this chlorotoluene. But where is the chlorine located? It's going to be by definition at position 2, because the methyl is going to be by definition at position 1 in toluene. So we'd get 2-chlorotoluene. Okay. Awesome use of the name. Fantastic. Kind of, sort of? Okay. Next thing I want to address, just because we can be extra confusing, why the hell not? Okay. Let's tweak this structure a little bit. And I'm going to change the location of the chlorine. This one might start to shift back to the methane name, right? Okay, we have a 1-chloro, 1-phenyl methane. Right? So the longest carbon structure is the 1 carbon here. And then it has the substituent of the chlorine, the substituent of the phenyl. Again, this structure shows up so commonly that it actually gets named benzyl chloride, which is a whole nother level of fun. In that case, what we're saying is the most important thing is that it's a chloride, and that the substituent on that chloride is benzyl. Where did the methyl go? Where's the CH2? That whole piece is benzyl. Okay? And for those of you being like, that's irritating, yes, it is. Not to be confused with phenyl. Okay? Not to be confused with, throw on another one. Oops, I'm almost out of space. With this one, what's that one? Phenol. Okay? So there's a lot of common names that kind of pop up through the aromatic structure. Those common names are insanely frequently used. Okay? Kind of like water. Okay? So we have to be aware of them. The ACS exam goes kind of back and forth on whether you're responsible for those or not. Okay? For the most part, you're not responsible for them. Okay? Or if you look at your multiple choice, it's clear that they aren't testing on that part of the name. Does that make sense? Okay. So be aware your nomenclature with aromatics can be a little bit dicey, but it does tend to follow the rules that we've already seen. Okay. So we're going to number where those locations are, and then we just kind of continue on. Mostly okay with that? Mostly. Okay. Where this can become fun is if we look at a strictly not IUPAC ruling. So if you're being asked to provide the IUPAC name, what we're about to reference does not count as a valid IUPAC name. Similar to cis and trans. Cis and trans aren't IUPAC. They're a way to reference where two groups are relative to each other on a pi bond. Okay? If I was to use IUPAC to name a cis-trans compound, what would I use instead of cis and trans? Technically, Z and E on Z same side for cis, and trans is E, right? Okay, so let's take a look at this structure. The chlorine is now a placeholder, and what we're going to talk about is a second group. Where's that second group located? If I put that second group there, okay, and we label it, that will be referenced as an ortho. Okay? And so what we're doing is referencing it towards the chlorine. It is that positioning that gets the ortho. Yeah? I'm sure there's a Latin root reference there that would make sense, but it doesn't make sense to me. Okay? Stop using words with ortho in it, because it's not helping. Okay. Ortho is too many letters, so we often refer to it as
Oh,
just O. So we'll see that reference. Okay. Molecules can spin, flip, rotate, and all that fun jazz, right?
Those are like feet, and I'm like orthopedic surgeon.
Just.
Oh, no.
Is there a position similar to that ortho?
on the other side.
On the other side, over here? We're looking at the same relative position to the chlorine. That is also an ortho position. Okay? What's the next position? Meta or M? Is there another meta? Yep, over here is our meta. And then lastly, we get para. Okay? So it's just a way to show the relationship between any two groups. It should not be used for nomenclature. If it was nomenclature, what would I be using instead of ortho? What?
Substitute priority.
Two, yes, or saying 2 or 2, that can't be true, because if I go through a number, if this is 1 and that is 2, this can also not be 2. Continue your counting around 4, 5, 6. Your ortho is the 2 and 6 positions. Your meta is the 3 and 5, and your para is the 4. Kind of, sort of? You get it? Okay.
Does ACS do that? Because I've seen them use.
ACS will use it, but it's usually as a red herring answer, which is extra irritating. I'm horrible with mnemonics. Yeah, and I got it. I had to process. So what she's talking about is where's the ortho position. So we're talking about some eyes, right? These little eyeballs. Okay. And then we get kind of the mouth. I'm taking a little bit of artistic liberty here. Right? That kind of... That's fine with me. The one problem that I would have with that reference, right, and this is actually why this one was on here, right, is that if we go back and use that back on the other structure, what I will get students telling me is that chlorine is located where on this first structure? Well, the chlorine is at the eyes, so that's the ortho position.
That's their problem.
Okay, and yes, for those being like, that's their problem, okay. Way to be understanding, guys. Okay? But do you at least see what I'm talking about? Okay? Our referencing is, when we talk about ortho, meta, and para, is typically where we have our substituent straight up, and that's why we go eyes, mouth, tongue. P can't be tongue. We just say that's tongue? Is that what we're doing? Okay, that's fine. Okay? The problem with that is that when we turn here, now your eyes, mouth, and tongue must also turn, right? Everybody understand that?
It's just looking sideways.
Okay. Okay, just looking sideways, just for you.
He's upside down.
Okay, so we have to be a little bit careful on that referencing. Does that make sense? Okay, so the ortho, meta, and para will always change depending on what your focal point is. We good? Okay. And we'll come back to that because we will reference those positions later. So some compounds, there's common names associated with them. So we've got a big list of compounds that have those common names. We already addressed toluene. Phenol showed up, okay, already. You're responsible for phenol. Toluene's a little bit weird, but that shows up so frequently that, again, people tend to pick that one up. The rest of them, okay, what about them necessarily triggers you to remember those names? okay? Much the same way as H2O is referenced as water, a lot of these names are just kind of arbitrary. Okay, make sense? So be aware they may show up. If they show up on the final, okay, I do temper those questions. I look more carefully at them to see if you're getting them wrong, and if you're consistently getting them wrong, I take steps to alleviate that as a negative against you. Does that make sense? Fine. TNT. What's TNT?
Dynamite.
Yeah? Dynamite doesn't sound like TNT though, right? So what is TNT?
HNO3.
Try nitro toluene.
So what's HNO3?
I'll answer that in a second. So, trinitrotoluene. Did it have to be organized in that fashion with the nitros at those positions? Nothing about the name as written TNT reveals that information, okay? But that is the easiest way to put those nitros on there. How do I know that? I've studied the rest of the chemistry we haven't talked about yet this semester. Okay? So we'll address some of those locations. As to what HNO3 is, it's nitric acid, and I'm not sure I understand the reference to here.
I thought that's what's used in like bombs.
I know what you're referencing there also, but different system. Okay, so spectroscopy of aromatics. Real quickly, the 3000 range, right above 3000 are CHSP2s. That's a big red flag, okay, for CHSP2. That does show up with aromatics, but it also shows up with alkenes. The rest of the, well actually, 1450 to 1650, you've probably also been looking for the carbon-carbon double bonds of the aromatics. You've probably not been looking at the 1700 to 2000, and you've probably not been looking at the bottom two. Why not the bottom two? Fingerprint region, so you ignored them. That doesn't mean there's not information in there. There is useful information there, it's just harder to see. 1700 to 2000. Did you hear anything about that range? Okay, those are overtones. They're difficult signals to pick out, but there is distinct peak patterning there that if you study IR and you have an aromatic compound, you can look at the IR and be like, oh, that's disubstituted. They're right next to each other. Okay, that's tri-substituted. That's everything is substituted just by looking at that range. That requires a lot more in-depth knowledge behind it, so it's up to you if you want to dig in there. Okay, to get you an idea, here's our 900 to 700 range. So what you're looking at is a strong peak and a medium peak. So a strong peak about, what is that, 875, and a medium peak about 690. That means you're tri-substituted at the 135 positions. Is that easy to pick out? No, it's insanely difficult because it's in the fingerprint region. If we take a look at that 2000 to 1700 range, again, you can see what peak patterning you'd see there. The intensities behind those, okay, are in the 2 to 3%. Okay? Your carbonyl is like 100%. Your CHSP3s are in the sometimes 10 to 70%. These peak patternings are in the 3 to 5% intensity range. So very, 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 very weak. Okay? But they are there, and sometimes you can pick them out. Come on. We look at HNMR. Because it's a benzene, as soon as you think you have a benzene structure, that's huge because you now have a large part of your structure. Okay? And it also limits where you can place things. Okay? There's only 6 spots now where you can place substituents around that ring structure. So if you have a familiarity with all of the possible patterns that you can arrange, you can recognize very quickly from looking at the spectra which patterning you've got. Okay? That requires a little bit of practice that I would say pushes back into OChem 1 with spectroscopy. So we're not going to look at it a whole lot here, but this is referencing the number of signals that you would expect in a carbon NMR. Okay? We can also do it for HNMR. The big example that gets very often referenced would be a structure like this. Right, if I looked at HNMR, how many signals would I be expected to see? Two. There's symmetry through that molecule. Due to that symmetry, the hydrogens across the structure are identical. That was an awful looking hydrogen. So I see two signals, one for the purple, one for the red. Okay, so those will show up in a very clean section in the 7 range, which typically is only for aromatics. So if I see two signals there, that's a big tip-off that I have an aromatic that has those groups substituted directly opposite each other. Okay, that could be helpful. There are other substitution patterns that could generate too. So we could push that a bit further. How many neighbors does the red hydrogen have? One neighbor, which means how many peaks? 2 peaks. Okay? In NMR lingo, what do we reference if we have a signal with 2 peaks? It would be a doublet. Okay? How many neighbors does the purple one have? Also 1, which means also a doublet. So what you will hear reference to incorrectly is a doublet of doublets. This is not a doublet of doublets. Okay? Doublet of doublets, if you don't understand, that's okay, but it's a much more complex splitting pattern. This is 2 doublets. Okay? 2 doublets in that 7 range means you have a benzene ring that is di-substituted where those things are opposite each other. Okay? You could go through and test this for, say, this guy. Okay? What would happen there? What would we expect to see? That's a bad one because they're all different. Every single one of those is different, right? So how many hydrogen signals should we see? 6? Are there any hydrogens up here? I would see 4 signals. Okay. What if I did this one? Red box. How many hydrogen signals would I see? 2. Okay. There is that symmetry through the middle of the structure. So those show up. Okay, as 2s. Then that's 3 and 3. What would my splitting pattern be?
2 doublets.
This one's also 2 doublets. Okay. So by looking at some of these patterns, you can start to predict very quickly what you would expect to see in the HNMR. Does that kind of make sense? That's your confidence level, how you feel you want to deal with spectra. Okay. But you can, with a little bit of effort, pick up some common patterns. Okay? With that, what we're going to do is move to kind of skipping along to our aromatic, anti-aromatic, and non-aromatic, which was the play posit that you should have all watched. Okay? That play posit was establishing what these rules are. Okay? These come from observations in the field of molecules and noticing that certain molecules were very, very, very incredibly stable or incredibly unstable based off of predictions of the energies of those bonds. Okay? And that's stable aromatics, unstable anti-aromatics, and then just irrelevant because it matched with our predictions, non-aromatic. So there were certain rules and patterns that came out of those. Okay? Huckel's rule, odd number of electron pairs. You'll sometimes see this reference of 4n plus 2. Okay? What is n?
Number of electrons.
Nope. Nope. Any whole number integer. Right, that's it. It's not associated with the number of electrons, anything else. It's just a number. Okay? But 4n plus 2, that equals the number of electrons in an aromatic compound. Okay? So the n doesn't really have any meaning except to be it's a whole number integer. Okay? But that calculation results in your pi electrons.
So how do we figure out what n
what you would do is count out your electrons in your structure and say, revert back and try and solve for n. If n was a whole number integer, it's aromatic. Okay? So let's take a swing at it with, let's say I've got my structure of benzene. Is benzene aromatic?
Yes.
Let's prove it. Right? Fully conjugated ring with overlapping p orbitals. Does every carbon have the ability to do resonance around the ring?
Yes.
Yes. So yes, that's true. So now we move to Huckel's rule. I want to know the number of electrons in that system. So how many electrons are in the pi system? 6. Okay. 2, 4, 6. I'm not referencing the purple bonds because the purple bonds are sigma bonds. Okay? I don't care about the sigma bonds. I only care about the pi ones. So there's 6 pi electrons there. How does that satisfy the rule? So what I would do is say 6 equals 4n plus 2. N equals 1. Is n, or is 1 a whole number integer? Yes. What does that mean? That's aromatic. Okay? So the n is just a solve out of the equation that you're coming from. That's why I said it doesn't really hold a meaning as number of electrons or pi bonds or any of that. It's just a number. Okay? And as long as that number is a whole number integer, that expression becomes true and everything's good.
Are there any exceptions?
No. Right? We'll continue to talk about it and you can ask me later. Right? So we could go through and do n equals 1, 2, or we could solve all this. What are the odds we're going to give you a structure with n equals 4? How many electrons would there be?
20.
So 4 times 4?
16.
16 plus 2?
18.
18. I need a structure with 18 pi electrons. How many double bonds is that? 9 double bonds. How many of you can draw easily a 9 double bond structure?
Easy peasy.
Right? That becomes challenging, which means you likely aren't going to see an n equals 4. Right? How about an n equals 0? Could we draw a structure with just 1 pi bond?
Yes.
Yeah, that's pretty easy. Right? How many electrons would be in that structure if we had n equals 0? 2. What if n was 1?
We just did it.
6. N was 2. 10. N was 3.
14.
14. Memorize 2, 6, 10, 14. Done. Those are going to be the most commonly tested on for aromatic structures. Okay? The formula is useful and that would allow you to propagate out to larger structures. The odds of getting asked about those larger structures are diminishingly small. Does that make sense? Right. Same kind of thing happens with anti-aromatic compounds, except anti-aromatic compounds, instead of this odd number of electron pairs, it's an even number. So now the formula becomes 4n, where n is 0, 1, 2, 3, so same deal. Right. If that becomes true, then it's an anti-aromatic compound. So what are the possible electrons I could see in an anti-aromatic compound? If n was 0, I would have 0, which is then going to be irrelevant anyway. N was 1, 4, n was 2,
Multiples of 4.
multiples of 4, 4, 8, 12. Okay? So half of your odd numbers are aromatic, half of them are anti-aromatic. As long as you split them, you're okay. Kind of make sense? Non-aromatic, they invalidate the rules listed, or this one's particularly irritating, it's a trick question. Okay? Anti-aromatic is particularly unstable. So if the structure would align to be anti-aromatic, what it can do is change its shape a little bit such that it is not a fully conjugated ring. If it changes its shape, it no longer satisfies rule 1, and now it becomes non-aromatic. Right? That changing of shape is not an easy thing to determine, and it's usually done by evidence, experimental evidence. So if you were seeing a question that was pushing you to really go into that trick question area for non-aromatic, Okay, they're giving you a lot of experimental evidence. Okay? So, I don't remember how many of these were in the video. What do we think? So the first one should be so we'll call it A for aromatic. How about the next one?
The middle one?
Progressing left to right, right? So that one. That should be anti-aromatic. Why?
Because if you count the number of electrons.
The number of electrons is 4, and that matches our pattern for anti-aromatic. It doesn't fit the pattern for aromatic. Okay? That structure is so small, it can't tweak its geometry at all either, so it's stuck as being anti-aromatic. How about the next one? Non-aromatic. Why is it non? That carbon has to be sp2. We have to have a p orbital to pass electrons through. We don't have resonance all the way around the ring. Next one. Anti-aromatic. Why'd you say anti? I think that was you, Milan. Does it still have resonance? Can that pi bond move to be here?
Yeah.
Yeah. That's missing electrons. I can fit electrons there. Okay? I can do resonance around the entire structure. So it does satisfy that overlapping ring structure with, or fully conjugated ring with pi electrons. Does it meet Huckel's rule?
Yeah.
How many electrons does it have in it?
4.
4. Huckel's rule was
4n.
2, 6, 10. 4n plus 2.
4 aromatic.
So that means this one is anti-aromatic. So what? And this is why memorizing those rules can become challenging.
So
Aromatic 2, 6, 10. Anti-aromatic 4, 8, 12. This one has 4 electrons. Anti-aromatic.
so 4n is not Huckel.
4n is not Huckel's. Huckel's is 4n plus 2. Next one. Non is not a ring. Next one.
No.
Why do you want to say none?
And oxygen.
What about the oxygen?
You can't resonance with them.
Okay, so no oxygen resonance. Anybody want to challenge? Yeah?
Fatally one.
Do I have resonance? Yes. Okay, so not aromatic doesn't work here, at least for that reasoning. We do have that resonance. So now the question would be Huckel's rule. Okay, how many pi electrons are there? Okay, so we're hearing an argument for 4. So we said it's not non-aromatic. It must be anti-aromatic because there's only 4 pi electrons. What did you move right there? A non-bonding pair. Where? Where did it end up? In a pi bond, which means that non-bonding pair of electrons moved into a pi bond, making it pi electrons, which means how many electrons are in that pi system? There are actually 6 pi electrons in that. This one is aromatic. Okay? So when we're talking about overlapping p orbitals, one of the tricky things is sp3 atoms can contribute electrons in, but we have to have that lone pair. Isn't there a second lone pair? Wouldn't that contribute in also and make it 8? How many can you contribute in any one instant? Only 2. The other lone pair, the instant the first one moves into the pi system, moves into an orthogonal or perpendicular orbital, which means it can't contribute to the pi system. Okay, so I only count one of them. How about the last one? Why are we saying anti? I don't know what same thing means. So you're saying pi, there's 2, 4, 2, 4, 6, and then you're saying 8?
Yeah.
Those are sp2. That last lone pair that I just drew, same deal, perpendicular orbitals of the pi system. This is where molecular orbital theory and hybridization comes in, understanding where those electrons are located. Those electrons cannot contribute to the pi system, which means they aren't part of it. How many electrons are in the pi system? There's 6 electrons in the pi system, which means it's aromatic. Okay? So when thinking about this, count your pi bonds, those are fine. sp3 atoms can contribute 1 pair of electrons. No other atom can contribute electrons. Okay? So pi bonds, sp3 atoms with one lone or with a lone pair, they can contribute 1. sp2 atoms aren't sp3, they can't contribute that pair of electrons. Okay? Something to consider is looking at something like this, which is a giant mess that we won't worry about. Okay? But where I will end is looking at why this is important, the reactivity between these two structures. Okay? Nitrogen typically acts as a base. Which of those structures would you expect to be more basic, and why? We'll pick up with that answer on Wednesday.